Hello everyone. Today session will be about mobility prediction. So it's a logical use of the positioning systems. First, let's see what the terms of the predictions can be. So first you have the short term, which relies logically on trajectory modeling. So here you have your real trajectory. There you can extract the speed vector and try to infer where the people is going. Then you have the middle term prediction, which relies on learning with state and transitions models. That's the term we want to deepen here. And then we have the long term, which usually relies on cycles in the movements of people, so such as on the morning you leave home, then you go to work, then you go to eat to the restaurant, then you go back to work, and then you go back home. So these are patterns that we try to extract from your movements. So let's go back to the middle terms, since it's what we want to study for the context-aware applications. So as I said, we rely on states and transitions models such as Markov models, Bayesian networks, hidden Markov models, and so on. So all of these models, they use past observations to predict further moves. So it's the core principle of such algorithms, which are in the machine learning supervised algorithms. So what's a Markov model, since we will be starting with that? By definition, it's a stochastic process without memory. So it's stochastic because it's labeling its transitions with probabilities to be followed. So from one state you have some outgoing transitions, and each transition has a probability to be used by the by your subject of study. The transitions happen between pairs of states, so you have the source state and the destination state, and the next state only depends on the last one, since the Markov model is a process without memory. So you have no more than the last location as history. So if we try to apply the Markov model to mobility prediction, we can say the states of the model are the locations. So you have to discretize your environment. And the transitions will be the moves between the various locations and their probabilities. So let's say we have 4 sequences, 1, 2, 3, 4, which are, so P1 is the first, is location 1, P2 location 2, and so on. So this sequence is P1, P2, P3, P4. We have the second one with P1, P2, P3, P5. Third sequence is P1, P2, P4, P6. And the fourth sequence is P1, P2, P4. So we can extract the following model based on these sequences. So from the initial state, which is we are out of the system, probability to enter in location P1 is 1. You see that all sequences start with P1. Then from P1, all transitions lead to P2. So we have 1, the probability 1 to go from P1 to P2. Then from P2 we have 2 outgoing states as P3 and P4, 2 for each, so it's 0.5 probability to go to P3, 0.5 to go to P4. Then from P4 you have one occurrence to go out of the system, so it's the state F. One to go to P6 and the second one to go out of the system. So 1/3 to go from P4 to P6 and 2/3 to go from P4 to F. Then from P3 we have one outgoing state to one outgoing sequence to P5 and one to P4, so 1/2 to go to P5, 1/2 to go to P4. And from P6 we always go out of the system, so probability 1 from P6 to F, and same for P5, probability 1 to go from P5 to F. So the problem is the history, because sometimes it's better to be able to take into account a few past locations to improve the model accuracy. But using more than one state to determine the next one is not Markovian, so we have to find a trick. The trick is quite simple here. We label one model state with several physical states. So here are two examples with second order and third order models. So since we use the same sequences, we get these models. So from I, the initial state, we have probability 1 to see P1, P4. So you remember every sequence starts with P1, P4. Then the subsequent states must have the last part of the previous state common with the first part of the new state. So for order 2, my second state will be the first in the next model state. So from P1, P4 we have 1/2 to get to P2, P3 and 1/2 to get to P2, P4. From P2, P4 we have 1/2 probability to go to F and 1/2 to go to P4, P6. So again P4 is common here at the end, here at the beginning, and then from here 1 to go to F. From here we have 1/2 chance to go to P3, P4, 1/2 chance to go to P3, P5, and 1 to go to F from both these model states. With 3 it changes a bit, so you see that from the initial state we now have 2 outgoing edges, 1 to P1, P2, P3 and 1 to P1, P2, P4 with half a chance for each. Then for this one we have we see P2, P3 being here at the beginning of both outgoing states with half a chance, so for P2, P3, P5, P2, P3, P4 that then go out of the system. And here from this one we have half a chance to go to F and half a chance to go through P2, P4, P6 and then to the final state. What we see also is that before being able to determine the first step in the model, we have to collect 2 or 3 locations. Actually it's K related to the order of the model. So you introduce a delay in your mobility prediction and observation. So there is still a problem. So with a short history it's not accurate because you cannot distinguish between several paths, which would be easy to see with several locations, but not with only 1 or 2. while with a long history you have more states, because you have the combinations between the locations inside the model state labels, and you reduce the number of occurrences for each state, so you have lower chances to further observe a state, and you will delay k-1 moves your decision and observation. That's why you can use a combination of several k Markov models, such as the all k Markov model, to use the highest order possible when the prediction is possible. And if it's not possible with the highest order, you try the order -1, -2, and so on, until you can make a prediction. The problem is that sometimes the longest paths are not always the best, because they may not have many observations to back their credibility, and therefore it's the statistical weight of all of the transitions and states for the higher orders will be lower than for the lowest orders. We also can use Bayesian networks, so it's based on dependency graphs. So for mobility prediction, we can use a dependency graph between those measures, so the current location, the time of the day, the day of the week, and the current duration of stay in current location. Then we will have to select the next state following one strategy. So a simple strategy is to use the most probable transition, but sometimes it's not suitable. So if you have 9 times 0.099 probability and one outgoing transition with 0.109, it's almost the same probability. You only change by 1% between those ones and the most probable, and it's very low for each one. So do we really need to choose one of those outgoing locations? While with 0.49 and 0.51, it's still very close, 2%, but it's a high probability for both that could be used as outgoing transitions and states to prepare handoff of your service. And we can even more improve the strategy when we are dealing with multimedia streaming, which can use qualities thresholds in which you can choose to ignore the outgoing states if they have less than a first threshold of chance to be selected. Then above this threshold but below a second threshold, you can prefetch the basic quality of the stream, so less definition or codec with less quality. And above the second threshold, you put the full quality stream, and it's better. So it's these are the following models, which are based on Bayesian networks implemented based on K Markov models. So it's built as a K-order Markov model in which we add the day, the hour, and the duration to trigger handoff, we use a delay which is equal to 90% of the shortest times based on the previous observations. So you look at the durations of all the durations of the learning set, you order them by their value, and you take the limit of the 91st percent of all of these durations. And then we use a simple threshold, which is t, which triggers a transition, a selection of each transition greater than t in probability. So this is for the k-past. The k-to-1 past will address varying history size. It will include all k-past models from 1 to k, use the same delay and threshold parameters, and begin with the highest order. It tries a prediction. If it gets a result, it returns and stops. Else it will try the order n-1. And last, the k-to-1 past star, since the longest history is not always suitable due to its possible lack of learning data when building the model, it will aggregate several results, which are the results from the k-past from 1 to k with the same threshold and delay. The predictions are built for orders 1 to k build prediction sets, and we return the union of all sets as a result of the prediction.